explain, to understand like what the problem is even asking, and think about what really cleverly use the basic tools that you have to answer questions. But let's start off with something really straightforward. Billy it says here, this is a fundamental counting. So here's the example. Billy has 3 hats, 3 different colored hats, 2 shirts, and let's say 4 pairs of pants. 4 pairs of pants. Okay. The question is, and the hats and the shirts and the pants, they're all different colors, or they're all distinguishable. The question is, how many different outfits can Billy make? And I want you to really think about this and see if you can justify it. And you can message me in chat. I'll give you guys a few minutes to think about it. and then later, if somebody wants to explain how they got it, I'd be happy to let you guys explain. And by the way, those of you just joining the class, you can always message me through the chat, either privately, or you can also message everyone publicly. Just be careful when you select public or private, that's the one that you mean to do. So far I got one answer, one correct answer. And it's definitely okay to be wrong here. If you're not sure, also message me if you're not sure at all. And I'll give you some feedback. So sometimes somebody asked me a really good question. I'm not sure where to start. So sometimes if you encounter a problem and you have no idea like where to even start, a good strategy for problem solving is see if you can even solve just a simpler problem. So maybe rather than do 3 hats, 2 shirts, 4 pants, see if you can do one with just 3 hats and 2 shirts. See if you can visualize how that one would work out, and if you can then from there explain how it works. Awesome. Nice, Lydia. Those of you who gave me, if I ask you how did you get there, I am curious how you thought about that number. Awesome. I'm really happy a lot of people responded, and not a lot of people, not everybody got it. About half and half, I would say. I'm going to ask some people who got the answer if they want to volunteer. If you don't want to volunteer, absolutely no pressure to explain, but it's always nice when students pitch in.
I can explain if you want, or
Oh yeah, go ahead. Who was that?
Eddie.
Hey, okay, yeah. And you can also write on here if you want to annotate anything. Oh, sorry, my share needs to be reset.
Okay, well, the way I thought about it was I just figured out like how many combinations you could have with 2 shirts and 3 hats. So you could have one of the shirts with all 3 of the different hats, and that would be 3 different outfits. And then you could have the other shirt with all 3 of the different hats, and then that's 6 different outfits with just those. And then you can just multiply that by 4, because for the 4 pairs of pants, then you have the same combinations for each pair of pants.
Exactly. Nice. What would be a really nice visual way to see this?
You can draw it out.
Yeah, and do you guys remember? You might have seen this a long time ago. Do you remember a good a strategy for drawing something like this?
Like tree.
Yeah, exactly. Yeah, but hold on, both of you. Yeah, you can draw a tree. So yeah, and Eddie's description of kind of starting with the first 2 and thinking about those possibilities, I really like that. So yeah, start with the first 3 hats. So you have, like, let's say you know, you have hat 1, hat 2, and then hat 3. And then after you pick the hat, you have another choice to make, which shirt. So you can do, if you pick the first hat, you can do shirt 1, or you can do shirt 2. And the same thing on each of these. So shirt 1, shirt 2, and the same thing here. And so the way to interpret this tree so far is that we have 6 total branches, and a branch is something that starts from the very root of the tree that goes all the way to the end. So there's 6 different ways to get from the root all the way to the end. And each sort of entire branch represents a configuration of a hat and a shirt, a different hat and shirt you can put. And then, of course, the 4 pairs of pants, I won't draw it out. I won't write it out here, but there's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then so forth. Same thing. So in total, we'll see that we have 3 times 2 times 4, which is going to be 24 different configurations. Now, a lot of times, students, when they learn this topic, they start to make up rules like, okay, if this is the case, I need to multiply. If this is the case, I need to add. And then when they get to other problems, they'll be like, okay, do I need to add or multiply? That's the first question that they ask. Rather than do that, I don't think that's a good approach. I think that's a really that's an approach that can get you into a lot of trouble because you're not really thinking about what the problem, what the setup of the problem is, and you're not developing the intuition for it. Uh, so every time you have one of these problems, you should, before you say should I multiply or add, you should really ask yourself, what does the tree picture look like for this sort of setup? And we'll see in a few examples. Sometimes you'll have different collections of trees, and how to set up the different trees. But once you build your tree and you understand conceptually, without even drawing it necessarily down, you can sometimes still visualize it in your mind. It should give you a really good insight on what you need to actually do. But anyhow, this is the fundamental counting principle. I think if you've seen tree diagrams, that means you have seen the fundamental counting principle. All it's saying is that if you want to make a configuration where you have the complete configuration involves making several different, like choosing several different options, the total number of configurations, so the number of total configurations is equal to number of options for each category. So if you have a certain number of options for, let's say, the category of hats, category of so you have different categories, and each category has a number of options or a number of choices to make. So this is category 1. Options number 1, options 2, options, and you can keep going with the number of categories. So I'm calling them category because I don't want to call them choices, because choices sounds kind of like options. And we'll see different interpretations of this kind of overall framework. The other, do you guys watch any, do any of you watch any like time travel shows? Nate? Yeah, which one do you guys watch? Yeah, go ahead, Nate. Well, you can hit spacebar to unmute.
The second season of Umbrella Academy.
Oh, that was really good. If you guys haven't watched Umbrella Academy, I definitely recommend it. That was awesome. So Umbrella Academy, any of you watched Dark? That one's also it's quite a trip. Or even was it Avengers Endgame? There's some stuff, not to throw any spoilers, but there's some alternate universe type stuff. So in this topic, I really like to think about alternate universes to help me count the total number of possibilities. So when you pick a hat, you actually create 3 different universes, one where each version of you picked a different hat. And so I immediately see those 3 universes. And then the next decision you make, it splits up each of those 3 universes into another 2 universes, and so forth. So if you start thinking about this is actually something called the multiverse theory, and they like to throw it into a lot of sci-fi where, like, if you go back in time and you change something, you create a different multiverse, or every time you make a different decision, you can split off the universe a little bit. But it has this interpretation, and you can apply it to solve these sort of problems. Okay, so let's now apply this to this counting principle to a slightly different problem. there is a house with 3 different doors, like kitchen door, backyard door, and like side door or something. Like 3 doors on the exterior. And you have access any colors, and each door is going to be painted with a solid color. Any colors, any 4 colors from, let's say, red, green, yellow, blue. Okay. The question is, how many ways? And the door, each door will be. If you pick a color, you have to paint that door. You have to use that color for the entire door. So you're not mixing colors or anything like that. So the question is, how many ways?
Can all the doors be one color?
Yes, you can repeat colors as much as you want. This
Okay.
painter has access to unlimited paint from each color. So how many ways to paint the house? And it's a simple problem, but a lot of students, about, I would say 60–70% of students miss the answer here. And really think carefully about how this applies to the previous one, if it's similar at all to the previous one.
Well, it has the same like format.
Yeah, if we have different things to do and different choices to make.
When it says 3 doors, do we have to paint both sides of the door?
Yes, so if you choose red for the first door, that means that both sides of the door will be red.
Does that change the question at all, or no?
No, no, no. Or if you prefer, I can just say it's the outside of the door. And for me, it really helps to think of the multiverse when I'm doing this one. Awesome. Griffin, you got it? David, nice. So far, about half and half. So those of you who I wrote good mistake, I'm very happy with the mistake that you made, because that's a very, very common one. See if you can think about how your setup is a little bit off, and and how it's not exactly the same as just the first problem. Yeah, go for it now. Adam, sorry, I got you unmuted here.
Okay. Should I do it now?
Yeah, go for it.
Okay. So yeah, my answer was 64, which is 4 to the power of 3, because so basically I first thought of it like, because if the first door there's 4 possibilities, and then I know you're supposed to multiply it with the next door, so it would be 4 times 4, because for each possibility, say if the first door is red, then the next door could either be red, green, yellow, or blue. So red has 4 possibilities under it, and then it's the same thing for green, yellow, and blue. So it's 4 times 4,
Nice.
and then it's just 4 times 4 times 4 when you include a third door. So it's 4 to the power of 3.
Awesome.
64.
Perfect. Nice. So does everyone see Adam's idea here? So I'm just going to kind of go through a little bit of the graph here, but obviously I'm not going to draw all of it. So a lot of students said 12, which is a very common answer. You can just see 4 and 3, say, oh, counting principle, I need to multiply the numbers. But make sure you really think about what's going on, and what the choices you're making, and what are the actual categories. And later we'll get into more complicated problems, and you really need to stop and think and see what is actually happening here. And sometimes it's like not very obvious what you need to do. And getting good at these is definitely a skill. And before I jump into like writing an equation or trying to think of the numbers, I do try to visualize like myself going through this setup and say, okay, well, the first thing I would do is go to the first door and pick a color. So once I pick a color, that means I've created 4 different universes for that first door. And then I think, oh, okay, now I see it. Then the next door, there's another 4 universes I can create, and so forth. So in total, it's going to be, 4 for the first door. So this is door 1. Then 4 for the second door, and then times 4, so door 2, and door 3. Okay. So there are, yeah. So that's how you could do that one. What else did I want to go through here? So just a quick application of this that I think you guys will find amusing, which I think also many of you know. Just hit yes if you have a 4-digit passcode on your iPhone or Android. And hit no, somebody who hit no. What kind of, do you guys have a 6-digit passcode, or do you have the? Okay, some people have 4-digit, looks like some people don't. So one question is, how many 4-digit passcodes are there? Like how many possible 4-digit passcodes are there? Does anyone know that one? If somebody was trying to crack your phone, how many different possibilities would they have to go through? Nice, Kieran, yes. It's 10,000. And one kind of cool way to see that, it's actually exactly analogous to this problem, is, well, how many choices are there for the first digit?
9.
Including 0, if you include 9, if you don't want to include 0 because it has to be like a whole number, you want it to be a 4-digit number, not including 0 as the first digit, then it's going to be 9. But if you include 0 as a possibility, there will be 10 choices. This is including 0. And then for the second digit is also 10. And then for the third digit, there's also 10 possibilities. And then the fourth digit, there's also 10, which is going to be 10 to the 4th. Now, of course, this should not be surprising, because what is the lowest number your passcode could be? What's the lowest possible passcode? All zeros, right? And what's the largest possible passcode? 999. Yeah. And so there's actually 10,000 numbers in here, because you have to remember to count 0 as a possible number, all zeros. So it's actually 10,000 possibilities. This kind of calculation is something people use when they want to determine the strength of a password. That's why they always ask you those really annoying things, like when you're making your password, please include like uppercase and exclamation point or like some symbol and a number. So that would just increase the total number, rather than just picking a digit or letter. If you just pick a letter, there's only 26 possibilities for each of these. But if you add in the possibility of using a symbol or a digit, you go from like 26 to 40 or something for each factor that you have in your password. So that's kind of why they really annoy you with those, and it turns out that it doesn't even do anything to secure your password, because they hack it in different ways. Nobody's trying to actually guess it by brute force. However, you could use this approach. I'm just going to ask you guys. How many passwords end with either a number, a digit from the set, so you're a spy and you saw somebody's like PIN and you saw the last 2 numbers, or you got a feeling for what the last 2 numbers could possibly be. They're either 3 or 7. It could be 3. You don't know exactly what the last 2 numbers. So how many 4-digit passwords? So how could we do this one? So the last digit could either be a 3 or a 7. Nice logic. 1 digit or 2. Sorry, I think I might have said it when I was talking the last 2 digits. So just the last digit has to be a 3 or a 7. But there's different ways of phrasing. It's nice. It'll be 2,000. Good. So there's 10 here, 10 here, 10 here, and the last one there's 2. So there's all sorts of ways to ask questions that are similar to this, which is 2,000. All right. Very good. Any questions on these ideas? Okay. The next is, again, the same. It's all about this tree diagram. Everything, I hope you'll see, like, at the end of this chapter, that everything is built on this question with Billy. Like, if you understand what Billy's question is about, you will understand everything else in this chapter. It's just about cleverly putting together the ideas that Billy is representing here. Okay, the next one is in a race with 10 racers, 10 runners, let's say. How many ways are there to assign gold, silver, and bronze? And we assume there's no ties. Nice, Kieran. Nice, Lacha. Jackson a bit lower. Alex a little bit higher. Nice, Chester. Rebecca, excellent. Okay, so let me see here. Oh, somebody got kicked out. Let me see here. Where's my participants on that? Wait, yeah, go for it.
Okay. I did it to where like how it was before with the digits where I set it up since there's gold, silver, and bronze. That means like I set it up like almost as if there's like 3 digits.
Mm-hmm.
And then the first one with gold, there's 10 possible runners who can get gold. And then for silver, since one person could already get gold, there would be 9 people who can get silver. And then
Awesome.
with bronze, there would be 8 people who could get bronze. And so I just multiplied 10 times 9 times 8 and got 720.
Excellent. Awesome. Thanks, Rebecca. Very good. And then do you see the tree diagram here is you have the 10 runners. And so let's say like they're Alice, Bob, Cindy, Dan. So for gold, you can have, there's 10 different universes that are made based on who got gold. And then for the silver, if Alice got gold, then there's going to be 9 runners left over. And the actual labels on the branches will be different, but the quantity, the number of branches that you can make after you pick a gold runner, after you already pick the gold, is always going to be 9 choices left over. So it's, you still take advantage of that structure, of that tree structure. Very good. Okay. And now let me ask a follow-up question to this one. So this is just 720. It's similar, the answer here is actually very similar to what it would have been for the house problem if I told you that once you use a color, you can't use that color again. So then it would be 4 times 3 times 2. So keep that in mind. If you're allowed to reuse a color or something like that, if you're allowed to reuse things, then it usually just turns out to be something with a power. But if you can't replace, and then each time you use one of your options, the following category might have one less option. Okay, now let's apply this to the following question. So, how many ways are there to rearrange the letters? By the way, let me just, oh, Lydia's in the class. How many ways are there to rearrange? Just hit yes if you are, and hit no if you don't. How many of you have like to play Scrabble or have played it before and know how the game works? And hit no if you don't play Scrabble either. Or even Words with Friends, it's the same thing. Okay, a few people haven't. So when you play Scrabble, you get the tile rack and you get your letters. And to help you see words, you sometimes just move them around while you're trying to find a different word. So how many ways are there to rearrange the letters A, B, C, D, E on the tile rack? So think about this one for a second, and then chat me when you have a good idea. Hi, Scriven. Oh, okay. You can tell Lydia that I will post the recording, so if she misses anything, she can catch up. And also you can definitely share with her what we covered here at the end. Great. Awesome. Nice, Melody. Okay. I'm seeing a lot of good questions. Okay, so I saw a few good ideas. One idea I saw was 5 to the 5th power, and I don't know if I made it entirely clear here, but this is like you have the letters A, B, C, D, E, and you just have to rearrange them. So 5 to the 5th power would be the case where, kind of like the one with the house, where you can reuse a letter as many times as you want, and you can only make a 5-letter word. So you can do like A, B, B, or A, B, C, A, B, or something like that. So that's what that would count. Here, it would be you would think of it very similar to the last problem with the race. Instead of gold, silver, bronze, now we have to make a choice for the first letter, for the second letter, for the third letter, fourth letter, and fifth letter. And just like the race, where each time you pick a letter, you can't use it anymore, because once you pick A, B, C, D for the first letter, the second letter can't be the one that you just picked. So the number of options that you have would always drop down by 1. So 5, 4, 3, 2, 1. And you multiply these all through. And this comes out to 120. And because this is something that shows up a lot in counting, it's the number of ways that we can rearrange 5 objects. If you had instead like 7 objects, you would do 7 times 6 times 5 times 4 times 3 times 1, all the way down. We have a name for this. This is called 5 factorial. So this is pronounced factorial. And the exclamation point reads 5 factorial. And this is also called a permutation. To permute things means to just rearrange or swap things around. So this is a permutation. Okay. Any questions on how we set this up as 5 times 4 times 3 times 2 times 1, and how it really comes from this gold, silver, bronze problem, but just rather than just giving gold, silver, bronze, you're actually talking about the number of ways to place everybody, like first place, second place, third place, all the way to last place. So it's like the complete version of the gold, silver, bronze problem. Any question about this one? Okay, so this is something that we're going to talk about a lot, or we're going to use this as a tool quite a bit whenever we want to talk about rearranging a set of objects, how many ways there are to rearrange something. Before we move forward, I'm just going to show you a little bit of algebra you can do, and a little bit of manipulations you can do with factorials and those types of symbols. So here's just some algebra with factorials. And they're actually, even though the numbers can get really big, factorials are very nice to work with. Here's one thing you can do with factorial. 8 factorial over 6 factorial. Do you need to spend a lot of time calculating 8 factorial and then 6 factorial? Do you actually need to multiply everything out? Or does anyone see a nice shortcut you can take here?
You can cancel out the factorials from top to bottom. So basically 6 through 1, top and bottom, so you'd just be left with 8 and 7 on the top.
Awesome, thank you. Yeah, that's perfect. So you can do, if you write them out without actually multiplying them through, you can see that the bigger factorial actually has the exact same numbers that the smaller one has, but a few extra ones. And so these will all cancel. And so dividing factorials is actually really, really nice. Look for a bunch of cancellation and just look for some things to be left over. So this is just going to be 56. So that's kind of a very useful thing with factorials. Of course, adding factorials, that's difficult because adding, that just gets, the numbers are really big. But when you're dividing them, there's usually a lot of cancellation that can simplify your work. And then here's a way to express it algebraically. Let's try this example. Let's simplify this algebraically. N plus 3 factorial divided by n plus 1 factorial. Now, I have an n plus 3 here, and it doesn't mean n factorial plus 3 factorial. What this notation means is the number in the parentheses, the n plus 3, that's the factorial that I'm actually going to take. And if n is, for example, if n was 5, then the expression that I just wrote down would be exactly the same as the expression above it. But if I want to do something just like in general with a random n, can I simplify this expression at all? Anyone want to try to explain?
Could you like the factorial like plus 3 and plus 2 and plus 1?
Nice. Yeah, it's a little bit weird. It's very good. We do n plus 3 because that's the first number. Whenever factorial, you always start with that first number, and then you just keep counting down. So it'd be n plus 3 times n plus 2 times n plus 1 times, what will be after n plus 1? Just n plus 0, just n or n, right? What about after n? what will show up? N minus 1. We just keep dropping 1 off from n. So it'll be n minus 1, n minus 2, and it actually keeps going. And here's the weird thing. Because you don't know where n is, you just kind of write something that's a little bit sloppy mathematically, but you just say eventually you're going to stop. And I just like to write 3 times 2 times 1. So I kind of assume that n is bigger, n is big enough that eventually it's going to hit 3, 2, 1. This doesn't quite work for like small n, but the idea, it helps you like visualize what's happening. So I keep counting down from n. And but the bottom one, though, starts off at n plus 1. Then it goes down to n minus 1. Oh, sorry, no. Then it goes down to n. Then it goes down to n minus 1. And then it goes down to n minus 2. And then it also keeps going all the way down to 3 times 2 times 1. And of course, there's n minus 3, n minus 4. Who knows how far down it goes? But we know it eventually has to stop. And then you look, these guys all cancel. So a lot of things will cancel. And you're just left with n plus 3 times n plus 2. And remember what we said, if n was equal to 5, you would get the same result. And you see here, if n is equal to 5, it works out exactly how we anticipated. And if you want, you can expand this. You don't have to. You could FOIL this out. N squared plus 5n plus 6. Okay. So that's a quick introduction to a little bit of algebra and how to work with these factorials. They're actually, they usually simplify to be pretty nice. Okay. Very good. So we did fundamental counting principle. We talked about how to count things when you want to rearrange them. And here we talked, and for number, for the one with the race, we talked about how to place things in gold, silver, bronze. And here we're talking about how many ways there are to rearrange somebody on the teller. So now, and we're moving pretty quickly through this. And so take some time this weekend to read the blog post, maybe watch this video, this class again, or at least, at the very least, think about what I'm about to go through. So the next question I want to ask you guys, and you might have seen it, but if you have seen it and you understand it very well, you can message me the answer. And if you know why the formula that you use actually works, then just message me the answer. But if you're not sure why the formula works, I really want you to spend some time to actually list out the possibilities to this following question. Let's say there are 5 people or you have 5 friends, but your couch in your living room, you can only watch TV if everyone's sitting on the couch. But your couch, and you're not going to sit, you have like your own chair, but your couch only has 3 seats. How many ways are there to pick 3 friends to watch Mulan with you? Are you guys excited for Mulan? Are any of you going to get it? I am excited for it, but I don't know if I want to pay $30 for it. But if I do invite a bunch of friends or have a friend who gets it, maybe we'll watch it with some family. Okay, so I'm actually going to ask you guys to think about, to list it out. See if you can figure out how to do this. This is not super obvious at all. So you have Alice, Bob, Cindy, Dan, and Evan. And you don't care how your friends sit. You just want to call them up and say, hey, Alice, Bob, and Dan, you guys want to come over? You don't care how, like, where they sit or whatever. That would just be one group of 3. Sabina, they're doing something different because the theaters are closed. They are releasing it like for $30 as an extra, and then in December it's going to be free for everyone with Disney Plus.
That's so stupid. If you're paying for the streaming platform, you should be able to like what anyway.
You know, they're clinging on to the old model. They don't want to give that up.
And it's just going to be like, I'm not really that excited for it personally because it's just going to be like normal Mulan except without the music and without Mushu, which are like the best parts of the whole movie anyway.
You know what? I really like normal Mulan, so my expectations are very tempered based on the previous live action Disney stuff. Okay, so for this one, try. I'm curious. I want to see you guys. I'll maybe put you guys into groups now. Actually, just write out. Let me just see here. Yeah, write out all the groups that you can come up with, and then compare with each other. If you're not sure how to do this with a formula or something, and you don't have a good reason for the formula, I want you to actually list them out. So, for example, one group is Alice, Bob, and Cindy. Another one is Alice, Cindy, and Dan, and so forth. See if you can do it in an organized way. Okay, yeah. Yeah, see if you can do it in an organized way. This is a little bit challenging. Well, let's do it to, I'll keep you guys in the whole thing. And then, please write them down and then tell me if you think you're close. And also, be, curious to share, see your notes on this as well. Question from Kalyana?
Yeah, are you just counting the groups of 3 that you can make, not like specifically who's in whatever seat?
Exactly. We don't care, like Alice, Bob, Cindy. I don't care if it's Cindy, Alice, Bob. I just want to know the group of 3. They're gonna sit how they want when they get there.
Okay.
So try listing them out. It's a good first approach. There's a few to list out. It's going to take a few minutes. But it is reasonable to list them out. It shouldn't take more than. And when you finish listing them out, Eddie, when you say including you, you're always going to be part of the group. So just like which group of 3 from the 5 friends? How many groups of 3?
Oh, okay. So you like have your own chair or something? You're not sitting on the couch?
That's right. You have your own chair. You're not on the couch.
Okay.
Yeah. Next question. Kalyan, did you have a question?
No, I think my hand just stayed up there, like when I asked the last question. Sorry.
Gotcha. Okay. No worries. That was only clear. Nice. All right, I'm getting a few students who are listing them all out. few people completed them. Does anyone want to share, like, did any of you who listed them out, did any of you who listed them out do it in some sort of organized way? Okay, so so I'm going to kind of go through a way of thinking about it, which hopefully you were able to list some of these out. I'm just going to list them all out. So we have Alice, Bob, Cindy. We have Alice, Cindy, Dan. And then if I miss one, I'm going to go through all of the groups that have Alice in it. So there's Alice, Bob, Cindy, Alice, Cindy, Dan. There's also Alice, Dan, and Evan. There's also Alice, Bob, and Dan. There's also Alice, did I get everybody? Bob, Dan, Cindy, Dan, Dan and Evan. Oh, Alice, Cindy, and Evan. Okay, thank you. So we got, I think that's everybody with Alice. Then, and if I keep them in order, I don't have to worry about going back. So I am ordering them, but I'm not going to re-include like Bob, Alice, Cindy. So now, how many ways can I pick people that have Bob as the first person? So I can do Bob, Cindy, Dan, Bob, Cindy, Evan, or Bob, Dan, Evan. Okay. Did I not get Alice, Bob, Evan here? I did not. Thank you. I missed that one. Okay, and then if I have to start with Cindy, I can't pick anyone before Cindy. I can also do Cindy, Dan, Evan. That's the only group of three I can pick. Do you guys think I missed any? Anyone see anything I missed? Does that match up with what you guys got?
Not allowed to like repeat combinations, right? Like we're making sure that we only have one. Like if I did Alice, Cindy, Bob, I can't do Cindy, Bob, Alice.
Exactly, because we're just talking about like which group of three you invited. We don't care about the order in which you invite them or how they sit there. We just want to know the group of three. So in total here, there's 10 groups, 10 different groups. If we had to do this question with 10 people, but now we have 2 couches with like 6 seats, so we have to pick 6 friends, six people out of 10 friends. You guys would agree that would be really annoying to write out the list for. Okay. So the question is, can we apply what we just learned in a clever, very clever way to actually get this number 10 by doing a calculation? And I'm going to tell you a funny joke, which a lot of students don't really find that funny, but it's a funny math joke. Mathematicians enjoy it. But it's usually like I just get not much laughter after this. But so here's how the joke works. There's a mathematician roaming the hills of Scotland with a shepherd. And the mathematician turns to the shepherd and he says, wow, I see you've got a wonderful flock of 25 sheep. And the shepherd's astounded. He's like, wow, how did you count the sheep so quickly? And the mathematician says, oh, that's pretty easy. I just counted 100 legs and I divided by 4. So the mathematician and shepherd joke. He counts 100 legs and divides by 4. I think this is one of the reasons I like this topic, is because I can tell this joke. But this joke is silly, but it actually holds a lot of truth about math and how mathematicians look at counting. Sometimes in math, it's very helpful to first count way over count by what you don't need, and then say, wait a second, I'm actually only interested in counting sheep, and each sheep I know consists of 4 legs, assuming they're all like healthy sheep. So therefore, I can actually figure out the number of sheep if I overcount the legs and adjust by dividing by 4. Sometimes in math, it's easier to overcount than count the actual quantities, actual groups themselves directly. So what might be an easier thing to count in this type of question that would actually be overcounting? What condition can I include that would maybe give us something that we could count very easily, and something that we actually did just a few minutes ago?
Not worrying about repeating people, so like ABC and ACB, counting them as separate.
Yes, exactly. So if we actually think about, okay, how many ways are there to pick somebody who sits on the left part of the sofa, the middle part, and then the right part, kind of like gold, silver, bronze. If we think about that at first, like Lasha suggested, then we know the answer to that. That's just 5 times 4 times 3. This is the ways to pick 3 people where the order matters. So pick 3 people, 3 out of 5, in order. Okay, now that's going to give us a pretty big number. What is that? That's 60 overall. So this is equal to 60. And that list of 60 groups of 3, it looks kind of like this, right? You can have Alice, Bob, Cindy. You can also have Cindy, Bob, and Alice. You can also have Alice, Cindy, and Bob. You can also have Cindy, Alice, Bob, Cindy, Bob, Alice. And lastly, oh no, I repeated that one. And lastly, you have Bob, Alice, Cindy, and Bob, Cindy, Alice. So in this group of 60, you have ABC, the group of 3 friends, rearranged 6 different times. And what technique could we use to, instead of like actually listing them out, how do we know ahead of time that this will be 6? Where does this come from?
You could use the tree, right?
The tree, or also this is just the rearrangements of 3 letters. The number of ways there are to rearrange 3 letters. That's just, we have a tool for that. That's just factorial. So Alice, Bob, Cindy, this can be arranged in 6 different ways, which is 3 factorial. So can Alice, Dan, and Bob. There's going to be another group of 6 as well. So in this list of 60 people, 60 different arrangements where the order matters, you can group them into groups that contain the same 3 letters, but just rearranged differently. And each of those groups always has to have a group of 6 rearrangements. And so if we're actually interested in ways to pick 3 friends, but we don't care about how they're ordered, we overcount first. The numerator is like counting the total number of legs, and the denominator is 321, which represents the number of ways to rearrange a group of 3. And if you look at what you get here, this is just going to be 60 divided by 6, and it comes out to 10. So spend a little time thinking about how this works and how it's really exactly connected to that joke with the sheep. And we're a little bit. Let's just do another 5 minutes. So this is called a combination. And is picking or choosing a group from a larger group and where the order doesn't matter. So let's say you have 7 people try out for the team, try out for a tennis team. With only 4 spots. How many possible teams are there? So try to work this out without a calculator and see if you can set it up just how we set up the one before. And the hint is also take advantage of cancellation. And message me when you get the answer. So, excellent. Okay, so I'm just going to share here the answer, but we'll go over more examples like this next time. So there's 7 people, and we have only 4 spots. So in the beginning, we overcount, where we can say who gets the first spot, who gets the second spot, who gets the third spot, and who gets the 4th spot. But at the same time, I don't care how they're ordered, because there's just a tennis team. There's no like, I guess there is first, single, second. There is the order in the tennis team, but I just want to know who overall makes the team. I don't care about their positions. So how many different teams can I make? So then I have to adjust by the arrangements, by rearrangements. And if I pick 4 people, this numerator overcounts it by 4 factorial. So 4, 3, 2, 1. And these are all just being multiplied. And then you simplify this. One nice thing with calculating these combinations is that you often don't need to actually calculate 7, 6, 5, 4, and also 4 factorial. Before you calculate, simplify. So 3, 2 cancels with a 6, and you're just left with 35. So this is called, there's 2 kind of notations for this. In some books, they write 7C5, means 7 choose 5. The notation that we're going to use is the one that's most common in more advanced math. It's 7 choose 5 where you kind of write it over each other, but you don't put a bar there. You just put them in parentheses. It's very easy to get mixed up when you're doing this and you think of it as a fraction, or you put the bar there because we're so used to writing like a bar between numbers when we write them on top of each other. So this is called, this is just the combination notation. We're going to use this one, but sometimes some books use 7C5. And so what we did earlier was a good example of combinations. This was 5, choose 3. Where was it? Ah, so the answer here would be 5, choose 3. All right, guys. So these are just some basic tools to help get you started with the homework. The homework is still going to be a little bit harder, but now you at least have all of the tools. You might need to kind of do some out-of-the-box thinking, and I encourage you to still do as much of the homework as you can, but now you have all the tools that you need to really attack the homework. And then on next Tuesday, we'll start going through more of the problems in the homework. And I encourage you to watch, like if you're a little bit shaky on this, the Khan Academy questions that I suggested are really good practice on kind of the basics of this idea. And we'll go dig deeper into these ideas. But do you guys have any question about what a combination is? And also now, do you feel, if you saw it before, hit yes if you feel like, hit yes if you feel like you have a better understanding of it, and hit no if you still don't quite get it. Cool, I'm glad a lot of people feel better about it. What is a GC?
Chat.
Yeah. You guys, if you post something, you're welcome to always post on the stream. Organize, make a group or something. That would be really good. Or yeah, you can send your number here. You could do like a Discord or something. Are any of you guys, do any of you have fun plans over the weekend? For the long weekend?
There's like an outdoor movie theater by my house, and they're playing The Princess Bride this weekend, and so me and my friends are gonna go and then drive up to Encinitas the next day because it's supposed to be like super hot, so we're gonna go to the beach.
Oh, it's gonna be another heat wave? Oh man. That sounds nice. I like Princess Bride. Yeah. I want to watch Tenet, but I don't know if I want to go into a movie theater. Working out, nice. All right, guys. So I'll keep the chat open if you want to collect the numbers. I don't know how you guys want to. If you guys are going to do a big message thread, I can see that. Make sure you turn off notifications or do something. Oh, scroll down. Okay. All right, guys. Have a wonderful rest of your weekend, and I'll see you on Tuesday.
Bye.
Bye.
Thank you.
Bye. Thank you.
Bye.
See you.
Thank you.
Thank you.
Bye, Rebecca. Bye, Sabina. Bye, Alex. See ya.
Professor,
Yeah.
I have a question about Khan Academy. It
Yeah,
says
definitely.
you added like me to a course, but it doesn't pop up. And
Yeah, you want to just share your screen?
all right,
Oh my gosh, I'm so sorry, Olivia. I made a mistake there. It's actually a 4. That's definitely my bad. I hope I didn't confuse everyone with that.
can I share the screen now?
Yes, go ahead.
All right, so basically it shows nothing. I joined the course. It does show me a notification though that you enrolled me for this course right here. But when I
Yes.
click it, it just leads me to nothing. Or it just leads me back to this.
Oh wait, can you hit courses? Go to see all 7.
This is something else. This is college admission stuff.
Oh, I see. Okay, okay. So weird. Let me see. Oh, maybe edit courses. Continue with one course. No, I see. No. And you saw where was that notification that I invited you?